Happy New Week, friends. We're going to have uh, a little bit more here on magnetism, and um, we will start celebration 2 on Thursday. That will be the pre-Thanksgiving week, and it'll go, uh, I think, through Tuesday. So you'll have a 5-day period to get that done. Um, Thanksgiving is Thursday, Friday of next week, and then we roll through into December, and then finals are hitting, and that's it. So let's get through a little bit more magnetism as we move along here. We're going to want to talk a little bit more about the effects of B fields on moving charges. So what we have here, I'm going to do another example. Since we know the force on a moving charge from a B field is the QV cross B force. What I want to do is an example called the velocity selector. And I'm actually going to chain this onto a mass spectrometer. So just like we did last time, we did the example of the mass spectrometer last time. So this is actually a really great addition to a mass spectrometer because it is able to, the velocity selector is able to control the speed that the charges are coming in. So essentially what's going on here is we're going to have so think back, okay, lab 2, where we had the filament, the heater filament, and the electrons came off and they got accelerated. They had an electric field that accelerated them. And then we put them through an electric field between 2 plates that caused them to deflect downwards. So same basic initial idea. In other words, a heater, and it's taking electrons off and accelerating them, or it's somehow accelerating ions that you have or something like that. And what we want to do now is put them through what's called a velocity selector so that they all come out with the same velocity. I'm going to make that a little bit longer. Okay, so here we have a set of parallel plates, and I'm going to put charges are going to come through here. They're going to come into here with a whole range of velocities. Okay, but they're going to come out of here with a 1. All right. In other words, from all of the incoming velocities, I'm going to pick one and allow those to go straight, and all the others are going to curve to the side. It's not that I'm going to change the velocities of these things. I'm just going to get rid of ones which have a velocity that is not the one that I'm asking for. So it's kind of like I don't know, you're police. You're at the side of the road with your radar and you're saying, which speeder do I want? That one. And you go, right? And you go get that one. I don't know, something like that. Anyways, we're going to cause all of the ones that do not have the velocity that we want to crash out of here. And only the ones that emerge are going to be the ones with the velocity we want, because they're the only ones that are able to travel in a straight line through this setup. So after that, we then have a setup here where we have a small hole, and then what we're going to do is we're going to send the ions into the hole, and there's going to be let's extend this down, and then there's going to be a magnetic field over here on the right side. I'll just say that the magnetic field is this, like that. Let's call this B number 2 out here. And then the ions are going to fly through here with speed v, and then we're going to say what happens. Okay, so we're going to go through here, and we're going to say, okay, I'm going to, suppose what I'm going to do is I'm going to hook these two plates to a battery, all right? And I'm going to put the positive charges down here, negative charges up on this plate here, so that I establish an electric field between the plates, okay? Like so. Let's also assume that these charges are positive just for ease of doing stuff right now. So there is the positive charge coming through. And so the electric field inside here is going to cause the positive charges to go curving upwards, right? Okay, so what we want to do now is, because we have a charged particle, what I want to do is take a magnetic field and put it in there with the electric field. And I'm going to have the magnetic field be just the right size so that a charged particle with speed v can go through in a straight line. All right, so this is the velocity selector part. And in a velocity selector, the goal is to have particles with a particular speed go through in a straight line. So what happens then is that the force upwards on the charged particles, right, is QE. Well, if we're going to have charges move through in a straight line, what must be the force direction produced by the B field? Well, we're going to want that. Okay. And we already know that down hat. Okay, we already know that the magnetic force we want to be going down. So which direction are we going to want the magnetic field to be going if I want the force to be going down? All right, so now it's time to be ready with your right hand here, and you're going to say, okay, the way that we've been doing it is fingers go with the velocity, and then you curl them in the direction of the field, but that's unknown. And then your thumb's going to point the force. Okay. So in this case, you're going to take your fingers are going to go with V, and we know we want V going to the right. All right. So I'm going to have V going to the right. Let's see here. V going to the right. Okay. I want thumb downwards. Okay. So which direction is the B field going to be pointed? If V to the right, thumb down, it's out. Okay, it's out. So the B field is out of the page. And that means I'm going to put a dot right here, call this B1. And you could look in over here at B2 and say, oh, look at the same thing. I've got a V going this way. I've got a B field outwards. So V, B down. So I know now that these particles are going to curve. There's going to be a force on them downwards. And these particles are going to curve around like this. Okay. So in this case, what we've got now is a downwards pointing B force due to an outward pointing B field. So this is the situation here where I have crossed fields. Okay, I've got those two fields going at the same time in the same space, and they are both forcing the charge. But notice that the force due to the magnetic field is velocity dependent. So all I have to do is pick what size B field I want to put there, and then that will determine what velocity I'm going to get, right? I can, or actually the easier thing is just get the electric field tuned to whatever is going to balance the force from the magnetic field. Because voltages are much easier to handle than B fields usually. So if this is the case, QE and QVB are equal. And so when you put a charged particle through a crossed field set, essentially you can have the fields determine, right? I can pick a velocity and say, what must my electric field be, right? Suppose that I have a magnet and I know it's magnetic field, and I say, and I want the velocity to be 5 times 10 to the fourth meters per second. So I multiply those and now my potential difference has to be this much. Or you could say, well, I've got these two E and B fields and I can't change them that easily. So what's the velocity that they're going to come out with? Well, it's going to be E divided by B. Okay. So if you look at this and you say, okay, well, what happens to the other particles, the ones that don't have that velocity? Well, you look at this force diagram. If they don't have that velocity, which force changes? Right? They're all coming through with the same positive charge, so the electric force is all the same. It must be the magnetic force that's changing because of the velocity in there. Okay. So when that happens, you're going to go look through and say, okay, well, if it's going slower, is the B field, is the B force bigger or smaller? Okay, the E force is always the same. But what if my velocity is less than the velocity that I'm selecting here? What happens to those particles? Well, if the velocity is lower, then you can see here that the magnetic force is not as big. Okay, if the magnetic force is not as big, that means that the electric force is going to be, it's going to be the same size as it was, but that means it's bigger. So it dominates, and these particles that are less are going to crash up here. If they're going through too fast, they're going to crash out down here. Okay, so you can go back and look at the forces. What's the effect of the forces on the direction of the which way the particle's going to go? Basically, if it doesn't have that right velocity, it's gonna go. Let's see, V larger, and here is V smaller, like that. Okay. Okay, then after we do that, what's going to happen is we're going to go into the mass spec part. Okay, now that we know the field here, it was, I should have called this B1, like so, right? Because we had E and B1. Now we're going to go into here where B2 is acting, and it happens to be in the same direction, causes the same deflection in the of the charged particles. So the F in this case, again, downwards. And then as it starts to turn, okay, the force is still perpendicular to the velocity and the field. And so as the velocity turns this way, right, V is kind of that way, V and then B outwards causes the force now to be that way. And then as V goes this way, same thing happens. And you go VB and the force is kind of up in this direction here. So it's kind of going this way. All right. So it goes along like that and causes it to turn. And then at least you've eliminated one possible variable in your mass spectrometer. So what you're going to do is you're going to have a little bucket right here, and you're going to collect all the particles with mass m. Now, what'll happen if the ions are heavier than that? Right. Well, they'll experience the same force, right? Because they have the same charge. They came through the velocity selector, so they have the same v. As they turn around here, the force is going to be the same, but it's going to be like a big truck trying to make a turn at a speed versus a small motorcycle making a turn at a speed, right? So if it's a larger mass, right, then it's going to make a larger circle, right? It's going to come way out over here, and it's going to end up somewhere down here. And of course, likewise on the other side, if it's a smaller mass, it's going to right like this. The force will affect it much more, and so it accelerates quicker, and the centripetal acceleration is much larger. So, and those two things you can kind of see. So I'll sketch those in green. So like that, smaller mass, larger mass. And the reason for that, you can kind of see from the idea of the centripetal force. So the B field provides a centripetal force, mv squared divided by r. Or if you like, ma, right? Where the a is just your centripetal acceleration term here. And that's the same for everything that comes through the slit into the magnetic field, B2, all right? The force is going to be the same. The force provided by B2 is going to be the same on every single particle that comes in here, because every single particle that comes in there has the same charge, and every single one has the same velocity, and it's the same magnetic field. So the force is the same for all particles. The question is, what happens to the acceleration? Well, if the mass is smaller, then the acceleration has to be bigger. And if the acceleration is bigger, that means r, well, because v is the same, right? So r is less. And likewise for the big masses. If you have a bigger mass, then a is lower. That's because r is bigger. So it looks kind of like this. Okay, so now if we do the centripetal analysis, now QV B2 is the force exerted by B2 on the charges, and that's going to be m times v squared over r. And the same thing happens here in the mass spec as did in the previous example, that we're going to have an r, if you like. If you want to solve for r, we can do that. It'll be mv over qb2. Okay. And v, of course, is related to b1, so there's that. All right, so that's a little bit more on what happens when you cross the fields, when you take electric fields and you put them here at right angles with the magnetic fields. You can get this velocity selector. So that's a pretty nifty idea. All right, so let's go down like this. Okay, so now what I'd like to do is talk about torque. Since we know that currents feel forces, like we did that example before of holding a weight aloft with a force due to a current running through a magnetic field. Now suppose I have suppose I now have a B field. Oops, a little bit bouncy there. Yeah. All right. Well, let's draw in a few more of those. Okay. So suppose I've got a B field here and I've got a current loop sitting in it, which is to say I'll idealize my current loop for the sake of the calculation of the torque. So let's make a rectangular current loop like that. And let's see, the halfway point looks to be somewhere about here. Like about like there. Okay, so let's call this dimension A, and let's call this dimension B. And let's suppose I've got a current going through it, which is going in a counterclockwise direction. So the current is going to the left here on the top, down, and to the right here on the bottom. So that'll be the direction of I. Alrighty. All right, so let's evaluate the torque that we've got on our current loop here. So the torque on the current loop depends on the forces that are being felt. So let's figure out what the forces are that we've got going here. I think rather than cluttering up this diagram a little bit more, I'm just going to draw the forces over here on a separate quick sketch here. So I'll draw the forces. My torque, my current is traveling around counterclockwise. So if the current, let's put that in. So if the current's going like this, like that through here. So now what are and the B field is going left to right. So now what are the forces on this thing? Well, forces on this thing would look like pretty straightforward. On the top and bottom, there's going to be zero force because there's no angle between, well, there's no perpendicular angle between the current and the B field. So if we want to draw forces, I need something that's going to give me a cross product. Oops, I need that over the L. That's okay. Force is IL cross B. And I can't do a cross product unless there's some perpendicular bits to the L and the B, right? IL times B perpendicular. Oops, B perpendicular. Or if you like, IL times B, and then there's a sine theta here, okay? Now note that your right-hand rule might work just great here, okay? Because you might be able to go, look, B is that way, and then the current is this way, so the force is out. No, it isn't, because there's no force. The sine of 180 degrees is zero. So anything that's completely parallel with the magnetic field is going to cause zero force on that current. So the force is zero on the top current branch and the lower current branch. So let's examine the sides. I've got the left side and the right side. And over here let's say over here on the left side, excuse me, over here on the left side, I'm going to have a IL cross B. So my force is going to be in the direction of I, which is downwards, B, which is to the right, and thumbs pointing out at me. So that's going to mean the force is out here. Force is coming out there. And I'd imagine, just based on a guess, that I didn't change anything except the direction of the current. So the force is probably in over there. Let's make sure. Up, curl, out. Well, I should say into the page. Sorry, into the page. And the force on let's call this the force on the right part. And this is the force on the left part. Okay. So the net force on the thing should be zero. is what it's looking like to me, because there's no forces on the upper or lower branches. The force on the left side and the force on the right side are of the same exact magnitude, just pointed in the opposite direction. So this current loop will not start traveling like this. There's no force on it that's net, but it does have a current, a torque, a couple on it. So the middle part here, it's going to, if we kind of axis it through there, it's going to, if we say pin it around the middle, right, make a pivot right there, it's going to start to spin. All right. And this is essentially the underpinnings of the DC motor. Okay. Your challenge, if you wish to make a DC motor, is to realize that as the current loop spins around, you have to reverse the directions of the current. Or said another way, you always have to have the current going up on the right side of the axis here, and you always have to have the current going down on the left side of the axis. So however you manage to do that, as long as you manage to do that, there will be a torque produced which results in a spin. So this is the kind of basic principle of the DC motor. Because as soon as you get to the, so suppose you didn't reverse them, right? If suppose you spin it around, and then what's going to happen? Well, then the forces are going to reverse, because if the right side and its current keeps going in the same direction and it comes over to this side, the current's going up on this side. Now it's getting pushed back the other way. So you're getting an oscillator rather than a spinner, rather than a motor. So anyways, let's look at the total torque on the current loop now. The torque's going to be the sum of torques, which is the torque on the upper half, the torque on the lower half, the torque, left part, torque on the bottom part. There we go, torque on the right part. And these, as we kind of already talked about, are both 0. All right, and I should have my vector sign here. Now we get to do another right-hand rule with the torque. So now we get to go from the pivot to where the force is acting. Just as you learned in 4A, you got R cross F, and that's the torque. So my pivot is going to be this dashed line here. And so we're going to go from the halfway point out to the force on the right, which is pushing into the page. So therefore the torque is up, causing the spin to be counterclockwise. If I was looking from above, it would be a counterclockwise spin. So the torque in this case is going to be 1/2 B. Let's suppose I'm going to find the torque on the right side here. The R is 1/2 B out to the force, and the force F is I times L, and the L of the side here is A, and B is the size of the field, and this is going to be in the up direction. Okay, the torque on the left side, of course, is going to be the exact same thing, right? Now I'm going R over to this way, and it's coming out of the page, but that still gives me a torque upwards because I reversed the force direction and I reversed the R, right? So instead of going out this way and in, now I'm going out the other way. And so anyway, it causes a counterclockwise spin as viewed from above. Yeah. So the total torque, so that's going to be equal to the torque on the left. And so if I add the two, I'm going to just multiply that by 2. Which is just B times IA capital B. And I'm going to rewrite that in a slightly more suggestive manner. I'm going to rewrite that as I times the product AB times B, like that. And I'm going to note that this little a times little b is actually the area of the loop. And from that, I'm going to generalize an answer here to the torque on a current loop in a magnetic field. So if you remember the idea of the normal vector, the unit normal vector from an area. Okay. So I'd like to define the unit normal to this area. All right. All right, our good old n hat. Well, I'd like to define the unit normal to this area. And so what I'd like to do is say, well, look, if I think of the unit normal as being perpendicular to the area of the loop, but also I've got the current in here. So if I take the current and I say, let's make the unit normal in a right-handed method with the current, because ultimately with an area, you could define one of two directions, right? You have your choice. I could say it's pointed out of the page, or I could say it's pointed into the page from this perspective. So I'm going to say, well, which one do I want to choose? I want to choose the one that's right-handed with the current. So how am I going to do that? Well, I'm going to curl my fingers with the direction of the current, right? So in this case, I'm going to curl my fingers counterclockwise, and then my thumb is going to point out of the page towards me. Well, anyway, it's going to point out of the page, right? So the unit normal n hat, make that a right-hand vector, and with the current. Okay, so that this will work for any shaped loop. It will actually work even if this is a circular loop. It's going to be great. So you take your current in the loop, you curl your fingers with the current in the loop, and then your thumb will point the right-handed vector that goes along with that. Okay, so in this case, n would be pointed out hat. All right. So I'm going to define a quantity called and this is no big deal really, but it's the exact same reasoning that we used if you look back on the dipole, torque on a dipole in an electric field. It's the exact same idea. I'm going to define a quantity which is I times A, well, in this case, I times AB, but really what I want to do is just call it I times the area. I times the area of the loop, n hat. Okay, I'm going to define this quantity. I'm going to say that essentially, when you cross that with the B field, is going to give you the torque. So check it. If I do that, then n, I'm going to use this diagram over here. I'm going to say n, it's rather large, but for a unit vector, but there it is. N is kind of pointing this way. So if I crossed n with B, n is pointed out of the page, B is pointed to the right. So if I go out, fingers with n, curl with B, then I'm going to get a thumb pointed upwards. And that's the right direction for the torque, right? The torque was upwards, causing in this case, because it started with 0 spin, it's going to cause the counterclockwise spin as viewed from above. Okay. So the torque is going to be up, and that's produced by crossing this n hat vector with the B field. So the n hat vector multiplied by I, the electric current, times the area of the loop, that makes a certain quantity, which we're going to call the magnetic moment. Okay, the magnetic moment we're going to say is equal to I, A, N hat, where N hat goes with the current right-handedly. Okay. That typically is known as the quantity of mu, like this. Mu is that, and therefore the torque on a current loop is generally written as mu cross B, because that n hat vector is the thing that gives the magnetic moment its vector nature. So n hat crossed with B gives you an upwards pointing torque. And so if you already had rotation, you'd know which direction the torque was anyway. Okay, so that is the torque on a current loop. Okay, where mu, the magnetic moment, is this thing that we've kind of run through here. Note that the similarity to the electric dipole, right? If you remember the electric dipole, because essentially that's what the magnetic moment is. The moment is the magnetic dipole, right? A current loop acts like a little magnet. For an electric dipole, it was the dipole moment crossed with the E field. So P cross E and mu cross B, it's a nice little similarity, okay? Essentially is what I would say there. Okay, so, oh, there's one other similarity that I could mention here. We also investigated the potential energy of a dipole in an electric field. You can also investigate the potential energy of the magnetic moment in a dipole. Sorry. You can investigate the potential energy of a magnetic moment in a B field and say, oh, well, is there a direction that has a lower amount of potential energy, et cetera, et cetera? And the answer essentially is yes. And it looks basically the same type of thing. So if you remember, it was the dot product of P and E. Well, the same thing would be true here, where we would look at the dot product of mu and B for the magnetic potential energy. Okay, so that notwithstanding, because we're not really going to do anything with that, I just thought I'd mention it. At this point, let's take a look back here. So at this point, I'm going to say that's the intro to magnetic forces. And what do we come out with? We've come out with a couple of general results. Let's see. So our results. The results were the second part of the Lorentz force law. Right, really kind of looking at what that term meant. So due to a B field only, this reduces to like so. And we looked at a couple of, well, we looked at mostly situations in which V was perpendicular to B. And I can do an example in the next section, in the next video of one in which it's not, but effectively it just introduces the sign of the angle between V and B. Okay, so the cross product just becomes this. We looked at currents. So that's the force on a moving charge by itself. If you have several moving charges, then you can call it a current, and it turns out to be the same essential idea. And so there's a force on a current from a magnetic field. We realized that there was a centripetal nature to the B force. If you think of the mass spectrometer and shooting in isolated charges, right? So you're going to talk about the centripetal force, which is kind of like the description of the circular motion that the charge makes, right? So the centripetal force, mv squared over r, is a net force. If you remember from 4A, this was one of the first forces that wasn't really a force, right? This is really a mass times an acceleration. This is a net force. So you can come out with things from that, which are called cyclotron quantities. And they're called cyclotron, right? Because that's what a cyclotron is. It's something that spins particles around in a circle. And that gives you a characteristic radius for what circle your charge is going to make for a given magnetic field. And essentially that's what all these massive colliders are doing. They're whipping the charges around in a circle, and then they get the beams going in opposite directions, and then they just try to crash them into each other to make a large center of mass energy. Let's see. The torque and things like that are kind of secondary results to these. Not that big of a deal for us right now, but can still be useful. The main results are these, I feel. V squared over r, and then what was the other one? Well, I can't remember. Anyways, okay. Oh, well, I guess I should also say that, you're gonna need to know the right-hand rule, the RHR. This is one of several right-hand rules that we're gonna be involved with. And you notice I just kind of used one to find the normal vector direction for that area. So there's going to be a couple of right-hand rules involved over the next couple weeks. So be prepared for that. Get your right hand all ready and set to go, because we will be using it quite a bit with different quantities. I think that's essentially all we have for now. Like I said, I can do one more example of charged particle motion in a magnetic field, and I'll just do that one in a separate video. But that'll do it for this for now, and then we'll have a lab on Tuesday, the 17th, in which we will go through kind of an exploratorium style lab for you to look at some of the effects that we're talking about and try to figure out, kind of in the same way that the electrostatic lab went. We're going to have the magnetostatic lab, where we're going to look at the effects of magnetic fields on moving charges and on currents. So we're going to see if we can't use the right-hand rule to predict what directions are going to occur and what size of things are going to move things where and what's going on. So hopefully you'll enjoy that, and I will see you next time.